Okay. So what is potential energy? Potential means it is not yet realized. It is potential. Okay. Stored energy. All right. So it is potential means unrealized energy. So what is it? When a body said to have a potential energy? You have studied it, right? Okay. Does it have potential energy right now? No? Now?
Yes. Yes.
So it has potential even now with respect to the ground. So it's a relative thing, right? So if I assume this is ground, this is surface. Okay, so it has no energy. Now I am working on this object against some force acting on it. Right? Is there any force acting on it apart from me, my force? Gravitational force, okay. So whenever you work on an object against some force acting on it, okay, so the whatever work is done by external agency, that gets stored into it as its energy. I worked on it, right, in raising it. So how much work I must have done? So first of all, what's the definition? It is the energy possessed by body by virtue of its position, okay, by virtue of its position or change of configuration. Or change of configuration. Right. So if I raise this object from ground, let's say it was here. Now I worked on it to move it by a distance, let's say from center, right? I moved it by distance h. Let us say its mass was or is m. So work done is equal to F(h). F must be at least mg.
Yes.
Okay. So whatever is its weight, if I apply equal amount of force, I'll be able to move it up. So I got mg on it, right? So this is the potential energy. How much is the potential energy? So will this work be the work done by external energy is engaged, therefore by me, right? But what is the work done by gravitational force? Minus mgh. Okay. But this is work done by me, so external energy, and this is also equal to potential energy. This is gravitational potential expression. You understand?
Yes.
What energy is potential energy? Work done by the external energy gets stored into it. So this is against the gravitational force. Meaning if there was no gravitational force, I can do work, okay, and that will not be stored into it as energy. Got it? For example, gravitational force is a different type of a force. Suppose I am working on it. Is it having potential energy? No. So am I working on it against some force? Yes, frictional force. But frictional force is not conservative force, because we need to be working against some conservative force. These concepts will be cleared in higher classes. So when the work is done against conservative force like gravitational, electromagnetic force, okay, then only potential energy or spring force. These forces are called conservative force. So just a keyword, in this standard it is not expected. Okay. All right. So when it will come again in higher class, you will come to know. Right. I'll just give a note on this so that like every work will not result into potential energy, like just I showed in case of frictional force. Right. So when work is done on a body against some conservative force, such as gravitational electromagnetic or spring force, electromagnetic, electric, electrostatic, or spring force. Okay. Then that work is stored in the body, the object, or in the body as its potential energy. So potential energies of various types, like this is called gravitational potential energy. Electrostatic, electrical force is there to charge between opposite charges. The force of attraction between positive and negative charge, or force of repulsion between same type of charge. So let us say this is a spring, okay? Right. And there is some ball on it. So when I press it down, right, what will happen? I worked on it. Okay, so when it is pressed down, so I did some work on it, right? So some energy is stored in it. Now when I release it, what will happen? Ball will fly. So right now there is some potential energy stored in it. That is elastic potential energy. When I release it, that elastic potential energy will be converted into its kinetic energy. Whatever is U here, on the way it will be kinetic. Got it? Always potential energy, right, will manifest itself in terms of kinetic energy. I did some work. Okay, when I release it, that's the kinetic. So you can verify that this H will be equal to half mv square. This is the velocity with which it hits the ground. Okay, so that's how it is conserved, right? Potential energy gets converted into kinetic, kinetic gets converted into potential. So energy is never created or destroyed. All right, so we discussed a bit about mechanical energy because a lot of students have questions on this. All other energy, I think you've already covered, right? Now tell me if you have any questions from previous chapters. Can I erase it?
Yes, sir.
Do you have any questions on this kinetic energy potentially? Because this bothers students, like most of the students have questions on this. Is it clear? Okay, let's forward. So magnetic effects of current. Do you have any questions from this? Anything from electricity, magnetic effects of current. First, there are any issues. Shall I quickly revise electricity?
Yes, sir.
So what is the first topic in electricity? It is electric current, right?
Yes, sir.
Everybody knows what it is. It is the rate of flow of charge, right? So Q by T, that's electric current, right? So if this is a conductor, so what is current? So if you consider any cross section, okay? So if Q amount of charge passes through it in time T, right? The Q amount of charge, net charge, because charges are flowing in this direction as well as in this direction. But there is a random flow. So net charge in one direction. Okay. It will depend upon what is the potential difference applied. Right? Without potential difference, there will be no current. Okay. And this current is flowing from positive to negative outside the circuit. And within the circuit, within the cell, negative to positive within the cell. Okay. And the current is because of flow of electrons, right? So where is electron flowing in this case? If this is positive, all the electrons will flow in this direction, correct?
Yes, sir.
So why the direction of current is shown I in this direction? Electron is flowing here, but we are saying current is flowing opposite to the direction. That's conventional. Okay. So by convention, right? We take that current will flow from high potential to low potential. It is by convention because in practice, always water flows from higher level to lower level, right?
Yes.
Okay, this is the general experience, right? Whenever you drop any object, it always goes from higher to lower. So by that logic, although electron flows from lower to higher potential, but we take the direction of conventional current. So this is conventional. Right? Okay, direction opposite to opposite to electron direction. So always remember this. Okay. So what is current? Net charge flowing through the cross-sectional area per unit time. Is it okay? Understood? So at any cross-section, right, this ratio will be constant throughout. Because current through the conductor is same at any given time, at any given point in time. Okay, so that was current. Now what is potential difference?
Charge. Current from one point.
Current. So let's say we have 2 points, A and B, okay? Let's say this point is A, B. This point is B. So what is the potential difference between A and B? B. Because B is applied, right? So we will say that the potential difference between point A and B is B, right? If work done, so what is B? It is the work done in taking a unit positive charge from A to B. Got it? What is potential difference? B. It is work done in taking unit positive charge between 2 points. Because potential difference is always between 2 points, right? So whatever work is done in moving unit positive charge between those 2 points is the potential difference between those points. Okay? So therefore, how do we derive the definition? So if in moving charge Q, right, work done is W. If in moving charge Q, right, work done is W. Therefore, in moving unit charge, work done will be what is it? W by Q. Unitary method. In moving charge Q, work done is W. The moving charge work done is W by Q.
Yes.
So this is nothing but potential difference, right? Therefore, V is equal to W by Q. Okay. So this is the definition of potential difference. This one.
Right.
ये किसके लिए था?
15 minutes are left.
So they give a Jyoti, this bell is for me. I don't think so. It is still 15, right?
Yes, sir. 15 minutes are left.
So this is the definition of potential difference, right? Next, we have Ohm's law, right?
Yes.
You were writing it?
Yes, sir.
You can write this one. Many people have the concept not clear on what is potential difference. So what is the source of potential difference? Cell, right? What provides potential difference? Cell. So cell is the source of electrical energy. It is the electrical energy which is working in moving the charge. So if you have not connected cell in the circuit, there will be no current. Okay. So current is the result of application of potential difference. All right. Now what is Ohm's law? So Ohm's law is, so now we know that current is due to potential difference. Ohm's law just says that if we increase the potential difference, the current will increase in direct proportion. Okay, provided the temperature of the conductor does not rise. Okay, so this is Ohm's law. So this is therefore, when you remove the proportionality, it will be constant times I. That constant is called as resistance of the conductor. Okay, that constant is resistance. So if you draw the VI graph, so since there is direct proportionality, when you increase voltage, your current should increase in direct proportion. So you should get a straight line. Okay. So when you take the slope, what is the slope of this? Slope is always ratio of change in y-axis versus change in x-axis, which is I. So what does this indicate? So slope is equal to delta V by delta I. So what is V upon I? Resistance. So R is equal to slope of V versus I graph. Okay, so resistance is the slope of V versus I graph, and it should be a straight line. So this is Ohm's law. Then what is resistance now? Resistance itself depends on the length of the conductor. Directly, right? If you increase the length, the resistance will increase with it in direct proportion, and it is inversely proportional to the area of cross section. So when you combine it, you will get it is proportional to L by A. When you remove the proportionality, you will get specific resistance or resistivity. Okay. So this is the expression for resistance. And what is specific resistivity?
The resistivity of the wire. Metal.
So it is nothing but resistance only. When L is 1 and A is 1. Okay. So specific resistivity of the wire is a characteristic constant for any given substance, whereas resistance is not a characteristic constant for a given substance. It changes with its dimension, length or area. So specific resistivity of a given substance always remains same, as long as the substance is same, right? And how do you define it? So specific resistivity is the resistance of conductor of unit length and unit area of cross section. Okay, so if you put L1 A1, rho is equal to 1. That's right. So resistivity of conductor is resistance of unit length and unit area of cross section. Since R is equal to, that is why. So here, unit of volt, I'm not giving the unit, you know the unit already, right? Volt, ampere, ohm, right? So what is unit of resistivity? Ohm meter, right? So this is equal to ohm meter. Then we have combination of resistances, which is
Series and parallel.
yes. So R series is sum of all the resistances, right? What is other thing in series? I is same throughout. Through all resistors. What is R parallel? So this is 1 by R1 plus 1 by R2. This is again a very common mistake. The final answer you must take reciprocal, right? So this thing is 1 by RP. So RP is 1 upon 1 by RP. Okay. So what is same here? Potential difference. V is same across all resistors. Okay. And you can write V is equal to V1 plus V2 plus V3. When you solve this, you get this. Here V is same and I is equal to I1 plus I2 plus I3. When you solve this will be V by RP, V by R1 like that. So just straight application of Ohms. Okay. This is about combination of resistance. What else you have here? Heating effect of current. So heat is energy, right?
Yes, sir.
So heating effect. So what is energy? So you know that work done in moving a charge through potential difference V is this, right?
Yes, sir.
So if this is the conductor across which the potential difference is V, for example. To move the charge from here to here, the work done will be QE. So this is the heat generated, right? And what is Q in terms of current? And let us say this was resulting into current I. Right? If this charge moved from one end to the other end in time t, then what will be I? What will be Q? IT.
IT.
Okay. So IT into V. So we just rearrange. So this will be E I into V. So this is the heat produced. So this work is energy, which is nothing but heat. So this work done shows up as heat. Right? Now V can be written as IR, right? Or H is equal to by Ohm's law V is IR. So this will be IR IT. This becomes I square RT. So it's quite simple if you know the logic of it. Okay. So it is I square RT. Now the last thing is power. Okay. So what is power? Work done for unit time. Right? Power is heat upon time. So VI. Power is equal to W by T, which is heat by T or energy by T, whatever, E by T. Whichever way the numerical is given to you. So what is E by T? I square R.
I square R.
I square R, because T went into denominator. Power in R. Or it is V square by R. Or so eliminate, right? What it will be? V square by R. R is equal to V by I. So VI. There are so many formulas. I square R, V square by R, and VI. Got it? Then depending upon the numerical, how the power is given in terms of everything can be. There are how many? 1, 2, 3, 4, 5, 6 interpretation of power. Okay?
Power is in watt.
Watt? Yes. Joule seconds. Joules per second. It's rate of work done. Right? So what is power basically? It is the rate at which energy is consumed or work is done. Unit is watt. What is unit of heat? Joule. Because it is energy. But power is joule per second, which is watt. And there are different units of power. Difference between kilowatt hour and kilowatt, is it? What is kWh and what is the difference between kilowatt hour and kilowatt? Is this clear? This is unit of electrical energy, commercial unit of electrical energy. You can say commercial unit. So when we get our electricity bill, we say itna unit, we have consumed so many unit, right? This is 1 unit. Okay, 1 electrical unit is 1 kilowatt hour. And what is kilowatt? This is unit of power, right? Power. So let's say you have a electrical device, say geyser of 1000 watt, that is, which is used for 1 hour. Then you will consume 1 kilowatt hour. Okay, got it? Or if you use 10 bulbs of 100 watt each simultaneously for an hour, you will consume 1 kilowatt. Okay, then there is one more unit of power which is horsepower, right? Have you heard
Yes.
about it?
Yes.
So 1 horsepower is just 746. 746. And what is 1 kilowatt hour? This is unit of energy, right? So what is it in joule? 1 kilowatt hour in joule. Yes, 1 kilowatt hour is equal to 1000 watt and 3600 seconds. So this is SI, right? So this can be straight away written as 3.6 into 10 raised to 6 joules. So once power is in SI, time is in SI, then you can write it straight into SI unit of energy. Because kilowatt hour is nothing but energy. It is what? Power into time. So what is power into time? Energy. Okay? So everything is, yeah, it's all interrelated. So in the next class, I think I will be getting one more class. In the next class, we will cover all the doubts on magnetic effects of electric. And any other doubt if you from this chapter, I will cover. This is it. What's the time? Stop sharing.